Welcome to episode 50, the retry trap, when stability breeds duplication. Have you ever hit a button twice because the first click didn't seem to work? Now, imagine that button charges your credit card. That's the core of what we're talking about today. In the world of complex software systems, we have something called a retry mechanism. It's a safety net. If a request to another service fails or times out, the system automatically tries again to ensure the operation completes. It's designed for stability and reliability. But here's the twist. This very mechanism, built to prevent failure, can sometimes be the cause of a major incident, like duplicate charges or executing the same critical action twice. This is a classic story of how good intentions in system design can lead to unexpected and chaotic outcomes. This is how major incidents are born. To really get our heads around this, let's step away from code and into the world of logistics. Imagine you run an online store. A customer places an order, and you dispatch a delivery truck. Your system is designed to wait for a delivery successful receipt from the truck. But what if that receipt never comes back? Your system, being diligent, thinks the delivery failed. So what does it do? It retries. It sends out a second truck with the exact same order. Now, let's consider why that receipt might not have arrived. It wasn't because the delivery failed. The first truck actually delivered the package perfectly. The problem was network latency, the digital equivalent of the delivery driver's confirmation. Message getting stuck in traffic on its way back to your warehouse. So now you have two trucks heading to the same customer with the same order. The original truck, which already delivered, and the retry truck. The customer ends up with two of the same item but was only supposed to get one. This is a perfect metaphor for what happens inside our software. A request is sent. The response gets lost or delayed. The system assumes failure, and it sends the exact same request again. The result? Duplicate processing. The downstream service, like our customer's house, receives the same order twice. This is where things get really interesting. In an ideal world, the customer would see the second truck arrive and say, "Wait a minute, I already received this," and reject the duplicate delivery. In system design, this is called idempotency. An idempotent system is smart enough to recognize a duplicate request. It sees the second delivery and knows it has already processed this exact order ID, so it simply acknowledges it without processing it again. It effectively says, "Yep, got it, already done," and prevents the duplicate action from occurring. This ensures that retrying a request has the same outcome as making the request just once, which is exactly the behavior we want. But without idempotency, our systems are like a clueless warehouse that just keeps sending out trucks, creating chaos, confusing customers, and messing up inventory. So let's drill down to the core insight here. The fundamental problem is what we can call undetectable remote failure. Your service calls another service over the network. There are three possible outcomes. 1, you get a success response. Great. 2, you get a clear failure response. Also good because you know what happened. But the third state is the dangerous one. Silence. A timeout. When a timeout happens, you are left in the dark. Did the request even reach the other service? Did it reach it and get processed, but the response was lost? Or did it reach it, and the other service crashed mid-process? You have absolutely no way of knowing for sure. You're flying blind. This uncertainty is the entire reason retry mechanisms exist. Because we can't know for sure, our best bet is often to just try again. But this decision inherently introduces the risk of duplication. If the original request actually did succeed, your retry is now a duplicate. It's a paradox. The action you take to ensure reliability retrying is the very thing that creates a new type of failure, duplicate execution. So you have undetectable failure on one hand and the inherent risk of duplication from retries on the other. When these two factors combine in a system that performs critical, non-idempotent actions like processing a payment, launching a nuclear missile, or dispensing medication, you have the perfect recipe for a catastrophic incident. A single timeout can cascade into a series of retries that corrupt data, charge customers multiple times, or trigger unintended real-world consequences. This leads us to a fascinating and crucial point. In many distributed systems, especially at massive scale, some level of duplication from retries is almost inevitable. You can't always guarantee that a message will be processed exactly once. The network is unreliable, services can fail in weird ways, and timeouts are a fact of life. So if we have to accept that duplication will sometimes happen, the question shifts. It's no longer, how do we prevent all duplicates? Instead, the more pragmatic and powerful question becomes, is there a property we can design into our systems that makes duplication harmless? Think about that for a moment. What if a duplicate request arriving at a service had no negative effect? What if the system could gracefully absorb duplicates as if they never happened? This property is the holy grail of resilient system design. It allows us to use aggressive retry strategies for high availability without constantly worrying about the side effects of duplicate processing. It transforms a potentially dangerous operation into a safe one. So, what is this magical property? What does a system with harmless duplication look like? That's exactly what we're going to explore next time. We dive deep into the patterns of idempotency and the specific design choices you can make to build truly fault-tolerant systems that can withstand the chaos of the real world. You won't want to miss it. Thanks for watching. If this sparked some ideas, hit that like button and be sure to subscribe so you don't miss our deep dive into idempotency. See you in the next one.